my dear students, welcome to Brahmastra 2.0 series. So last year we did Brahmastra series and it was very popular among students. So this year we thought why not bring it back, and we have added all the important questions that is already published by your PU board. So we have included the questions from your model question papers. We have also included the questions from your question bank as much as possible. Now, so this is the basically the summary of entire chapter with all the important questions from the chapter discussed in one single video. So if you watch this video, electric charges and fields, today I'm going to discuss then all of your queries, that what type of questions might come from this chapter, what are all the important derivations, what are all the important numerical questions, everything will be covered in this lecture from this. So this is the series that you must watch if you are preparing for the 100 out of 100 in your PU board, right? So without much delay, let me start with today's session. First, I am going to discuss about the blueprint. Now in the new blueprint, they have not given the separation between whether the question that is going to come, will it be a MCQ question or will it be a fill in the blanks question. So for the safer side, we are going to discuss everything. So one mark question will come. This may be an MCQ, that is 99% chance, because all the three model question papers giving you MCQ from this chapter. Now short answer type questions will be, there will be a 1 2 marker question from this chapter, there will be 1 3 marker question from this chapter, and there will be a long answer type question from this chapter. Now this long answer type can be a derivation, can be a numerical question, it can have both. Okay, last year's final board paper 5 mark numerical question came from this chapter, but this year there is a chance that 50% chance that this year there will be a derivation from this chapter and numerical question will come from the second chapter. Okay, so you have to prepare for everything. Okay, and those who somehow misses the first paper and want to improve in the second paper, then they have no other option, they have to prepare everything, 5 mark derivation, 5 mark numerical as well. Okay, now let's look into the questions that we are going to discuss. We are going to discuss 15 MCQs. We will be also discussing 5 fill in the blanks. We will be discussing short answer type questions 5. We will be discussing short answer type 3 marker question 5. We will be discussing 4 very important derivations from this chapter, and also we are going to discuss 6 numericals from this chapter. Okay, so if you watch this entire chapter will be covered through this one lecture. Now let's continue with the first question. The electric flux over a closed surface enclosing a charged particle is minus q by 6 epsilon naught. The charge of the particle is, so total charge enclosed, total electric flux is basically, we know that electric flux is given by charge enclosed divided by epsilon naught, and that value here, now let me write this like this so that there is no confusion. So charge enclosed divided by epsilon naught. So suppose there is a Gaussian surface and the charge which is enclosed inside it is QEN, then QEN by epsilon naught is the electric flux, and that is given by minus q by 6 epsilon naught. So if you compare these two, you get Q enclosed is equals to minus q by 6. So Q enclosed is minus q by 6, it is not any other value, so it will be minus q by 6. Option C is correct. Next question, the value of basic unit of charge is, so the basic unit of charge is 1 electron, charge of an electron, that is 1.6 into 10 to the power of minus 19. Now if you see the options, they have cleverly given 1.9 into 10 to the power of minus 16. So they just change the 6 and 9. So be careful, answer it, it's easy question. Now next, the SI unit of electric flux is, electric flux is given by electric field into area into cos theta, right? Now unit of electric field is Newton per Coulomb and area is meter square, and cos theta is a dimensionless quantity, so Newton per Coulomb meter square is the SI unit. So if you see the option C is again correct answer for this question as well. Now if you want to download the PDF of this lecture, and if you want to get all the updates that is happening related to your PU, related to KCET exam, related to Comet K exam or JEE or NEET, so if you want to get all the updates, then definitely you have to join our WhatsApp channel. Also the link of the PDF of this lecture will be available to you only through our WhatsApp channel, so don't forget to join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Also I would request you, if you have not yet subscribed to our channel, then don't forget to subscribe to our channel. All your PU and KCET related things will be covered in our channel exclusively, so don't forget to subscribe if you have not yet subscribed. Now let's move on to the questions. If a body contains n1 protons and n2 electrons, then the net charge of the body is. So very interesting question. This is from your this year's model question paper. So body contains n1 number of protons and n2 number of electrons. Now you might say, sir, which one is bigger, which one is smaller is not given. How can I calculate the net charge? No need. We know that charge of a proton is always positive. So what is the total charge of the protons? Total charge of the protons is number of protons times the charge of a proton. Now charge of a proton, interestingly, is same as charge of an electron. Only thing is they are positive. Okay, amount is same, only thing is proton is positive, electron is negative. So this is the total amount of charge of a proton. Now charges are additive in nature. So what is the total charge of electrons? Total charge of n2 number of electrons. Total charge of n2 number of electron is n2 into minus E. Why minus E? Because this is electrons. So electrons are negative in nature. So basically this question is being answered through the property of electric charge, that charges are additive in nature. So if you take n1 number of protons, n2 number of electrons, just multiply charges, individual charges, and add them. Also you have to take care of the sign of the charges. So if it is proton, then it will be positive. If it is electron, sign will be negative. So n1e minus n2e, or n1 minus n2 into e. So this is the total charge of the body. So n1 minus n2 into e. Now if n1 is bigger, then charge will be positive. If n1 is smaller, then charge will be negative. As simple as that. We do not need to know which one is bigger, which one is smaller to calculate the net charge. Okay, so this is the formula, this is the way you should solve this kind of question. This is a little tricky question, can be considered as a HOTS question. Now next, electric field due to an electric dipole at a distance small r on the axis of the dipole is. So electric field due to an electric dipole on the axis of a dipole is inversely proportional to 1 upon r cube, not 1 upon r square. So it is inversely proportional to r cube, inversely proportional to r cube. Okay, if you remember, electric field due to a dipole on its axis is given by 1 by 4 pi epsilon naught 2p by r cube. So electric field on the axis is inversely proportional to r cube. Now next question. The electrostatic force between a pair of unlike and like charges respectively. Again, this is from your latest model question paper. The electrostatic force between a pair of unlike and like charges. So what is between unlike charges? Unlike charges always attract each other and like charges always repel each other. So first is attractive, so unlike is attractive and like is repulsive. Okay, so attractive comma repulsive is the correct answer, just to test your patience, just to test your whether you are able to read properly and answer this question or not. Okay, now next question. Gauss's law is true for any surface only open surface, only closed surface, only spherical surface. Now 90% of you will blindly mark any surface, and that is not true. Gauss's law is true for only closed surface, and that closed surface can be anything. Okay, even if you consider a plate, okay, a plate that where you eat your lunch and dinner, that place is also a surface, but in that case that surface Gauss's law is not applicable. This is an open surface. A bowl, okay, if you are considering a bowl where you drink your soup or tea, so that is also can be considered a surface, but they are all open surfaces. As long as it's a closed surface, the shape of the surface does not matter, but closeness do matter. Okay, so be careful. Again, easy question, but again that can trick your mind. So it is only true for only closed surface. Next question, the SI unit of electric charge is Coulomb meter, Coulomb per meter, Coulomb. So SI unit of electric charge is Coulomb. The total electric flux through a closed surface in air is equal to 1 by epsilon naught times the total charge enclosed by that surface. This is the statement of Gauss's law of electrostatics. So Gauss's law of electrostatics is the correct answer. So option C is correct. Next question, the SI unit of surface charge density. This is one of your previous year questions. I think 2024 this question came. The SI unit of surface charge density is Coulomb per meter square. Coulomb per meter square. Okay, not Coulomb per meter cube, not Coulomb per meter, but it is Coulomb per meter square. SI unit of surface charge density. Line charge density Coulomb per meter, and volume charge density Coulomb per meter cube. SI unit of electric field Newton per Coulomb or volt per meter. There are two units of SI electric field. One is Coulomb, Newton per Coulomb, and second one is volt per meter. Both are SI units. Next, what is the nature of Gaussian surface involved in Gauss's law of electrostatic? Magnetic, scalar, vector, electrical. So the nature of Gaussian surface involved in the Gauss's law of electrostatic is a vector. Okay, that's why we take E dot dA. Okay, E dot A. So if you remember, flux is always E dot A. That means the surface has to be a vector quantity. Ea cos theta, it is a dot product. So surface has to be a vector quantity. If it is not a vector quantity, then Gauss's law will not be applicable. Okay. Now next question, the angle between the dipole moment and electric field at any point on the equatorial plane is. So the direction between dipole moment is always pointed from negative to positive, and the electric field along the equatorial plane, this is very special, it is directed exactly opposite to that. So dipole moment is from negative to positive, electric field is from positive to negative. So the angle between these two lines, when you draw from a single line, will give you 180 degrees. So correct answer is 180 degrees. For axial case, the angle is 0 degree. The dipole moment and electric field are in the same direction. So in that case, angle will be 0 degree. Now let's see question number 15. The torque acting on an electric dipole placed in an uniform electric field is maximum if the angle between the electric field and the dipole moment is 0, 60, 90 or 180. So now we know that torque acting on an electric dipole is given by tau equals to Pe sine theta. Now sine 0 is 0, sine 60 is root 3 by 2, sine 90 is 1, sine 180 is again 0. So that means the torque acting on this dipole will be maximum when sine theta value is maximum. Sine theta value is maximum when theta is equals to 90 degrees. So the torque acting on this dipole will be maximum when the angle is 90 degrees. Next question. Now we are solving 5 fill in the blanks. One of the basic properties of electric charge is dash, a pair of equal and opposite charges q and minus q separated by a distance 2a is an dipole. The electrostatic force between two charges is maximum in dash. Electric field inside a charged spherical conductor is 0. Two electric field lines will dash cross. So sometimes what happens, some of the fill in the blanks we can directly tell by reading it, okay, without even reading the options. Some of the fill in the blanks we do need options to answer. So first of all, you pick up the questions where you can directly answer the fill in the blanks. Okay, for example, I know this is this will be a dipole, okay, this will be a 0 and this will never cross. Okay, so these three are easily answerable. For remaining things we need to check the fill in options. So if you see the properties of charge, so never, dipole, quantization, vacuum, 0, always. So among these only quantization is the property of charge. So first option must be quantization. Second option, we have seen that a pair of opposite charges, equal and opposite charges separated by a small distance, so that must be dipole. You cross verify it once. Even if you are sure, you have to cross verify it once if the option is mentioned or not. Next, the electrostatic force between two charges is maximum in never, vacuum, 0, always. So from these options, remaining options, only vacuum is making some sense. We know that force between two charges is given by 1 by 4 pi epsilon naught q1 q2 by r square. So if you put them inside a dielectric, the force reduce. That means the force is maximum in vacuum, right? There is no medium or free space, right? So the option could be vacuum, option could be free space. So you have to check it once and confirm it. So the correct answer for this is vacuum. Electric field inside a charged spherical conductor is always 0. Okay, so this is obviously known answer. So we will see whether 0 is given or this is given, either Z E arrow given or this symbol is given. So you have to be careful and mark it correctly. Two electric field lines will never cross. So never is the obviously the answer, not always. Okay, two electric field lines never cross each other. So correct answer is never. Okay, so this is how you should tackle fill in the blanks. Fill in the blanks are the most easy part, but still student make small mistakes in fill in the blanks. And remember, if you make one mistake in fill in the blanks, there is a chance that two mistakes will be automatically happen. Okay, the options are given generally such a way that there may be some cases confusion between two options. So if you make one option wrong, then there is automatic wrong answer can be happen to the another question. Okay, so be careful for fill in the blanks, because if you make one mistake, there is a chance, high chance, that there will be two mistakes happening without you are realizing it. Okay, now let's move on to our next segment, 2 marker questions. State and explain Gauss's law in electrostatics. The most important question from this chapter. Gauss's law states that the total electric flux passing through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the closed surface. And its explanation is phi equals to q by epsilon naught. This is the flux through the surface, or E dot ds equals to q by epsilon naught. Q is total charge enclosed by surfaces. So here you have to draw a surface, name it S, and charge inside the surface you have to show it Q. Okay, so this is the total charge enclosed by the surface. Next question, write Coulomb's law in vector form, explain the terms, state and explain Coulomb's law. Now this question can be asked as a 3 marker, also it can be asked as a 2 marker question. Okay, so here we are discussing it as a 2 marker question, but same question can be asked as a 3 marker question. Statement, Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of magnitude of the 2 charges and inversely proportional to square of the distance between them. Coulomb's law in vector form is F equals to 1 by 4 pi epsilon naught q1 q2 by r square r cap. Now in this case you have to show what is the r cap vector. Okay, so you can take this as your r cap, and you have to mention this is minus r cap. Now obviously based on which F12 or F21 it can vary. Okay, this is the overall statement of Coulomb's law. And also you have to mention the terms. Q1, Q2 point charges, epsilon naught is permittivity of free space, r is distance between Q1 and Q2, r cap is the unit vector. Okay, now next, sketch the electric field lines for force due to a point charge if Q is less than 0, Q is greater than 0, or due to a dipole. Okay, so this question is a mix of your last year's model paper question and this year's model paper question. Okay, this year's model paper question, they have asked you to draw a due to a point charge, positive point charge and a dipole. Last year it was a negative charge, a positive charge, and dipole was not there. So if Q is less than 0, that means it is a negative charge. For a negative charge, all the field lines will converge at a point. So this is the, as you can see, this is negative charge, all the field lines are converging. For a positive charge, all the field lines are going away along the straight line. So you have to use a scale to draw this diagram. And for dipole that they have added, it's slightly tricky. So this will be a straight line, but remaining lines you have to draw using your hands, because even if you are using compass or scale, that will not be perfect, because there is no such, they are not circular, by the way. So these lines will not be circular. And you have to draw using your hands. Practice once or twice, it will be easy. Field lines will exit from positive and they will close at negative. Some field lines will go towards far away, and again it will come back to negative, but the connection you need not show. So 2 lines you show up, 2 lines you show down, and 2 lines you show going in this side, 2 lines you show going upside. Similarly, 2 lines coming from this side, 2 lines coming from this side. That's it. Okay, this is the electric field due to a dipole. Now next, define electric flux through an area element, mention its SI unit. This is a new question from your latest model paper. So definition of electric flux: the electric flux through an area element is the product of the dielectric field and the area vector, and it's represented the number of electric field lines passing normally through that area. Okay, so if you remember the diagram that is given in your textbook, this is how they have given it, right? Electric field lines, and some cases the field is not perpendicular, so in that case the theta angle was given. Okay, so phi is equal to E dot A, and it was given that this is the A vector, and the angle is given by this. Okay, so E dot A is EA cos theta. SI unit of electric flux is Newton meter square per Coulomb. Okay, Newton meter square per Coulomb, Newton per Coulomb meter square is also acceptable. Okay, so you have to remember the second line is slightly extra. You can mention it, you cannot, you may skip it, but you have to remember that electric flux through an area element is the product of electric field and the area vector, dot product or scalar product. Okay, it is the dot product, mention dot product. Okay, dot product or scalar product of the electric field and the area vector, and it represents the number of electric field lines passing normally through the area. Mathematically portion you can write, you can skip, not important, but SI unit as part of the question you have to answer it. Next, define electric field at a point. What is meant by source charge? Again, this is a question from your latest blueprint. Not blueprint, sorry, it is taken from your latest model paper. The electric field at a point is the net force experienced per unit positive test charge placed at that point in an electric field. Again, mathematically E is equal to F by Q. So force experienced by a test charge divided by its own value of the charge is the electric field at that particular point. Okay, and what is the source charge? The source charge is the charge that produces the electric field in the surrounding space. In other words, it is the original charge responsible for creating the electric field experienced by other test charges. So when I am saying that electric field, we do not mention any charge who creates it. So source charge is the original charge that creates that electric field. Okay, so suppose I say this is a source charge. Source charge means it will have its own electric field. Okay, and if you put a test charge over here, it will experience a force. Okay, from that force we can calculate the electric field at that point. Okay, so a test charge, if the same question is asked and they add what is a test charge. Test charge is a charge that do not produce any electric field of their own. Okay, test charge means it's an imaginary charge that do not produce any electric field of their own. Now let's move on to the 3 marker category. Derive the expression for torque on an electric dipole placed in an uniform electric field. Very, very important and classic question. Even this question is, even though this is a very old question, and still it is included in your this year's blueprint as well. So here we have 2 charges. Say this is plus, this is minus, plus Q, minus Q, and we are trying to find what is the torque acting on this dipole. Okay, dipole is basically 2 charges separated by a small distance, say 2a, and when you place in an uniform electric field, it will not experience any net force, only net torque it will experience. Now suppose the electric field is E. Electric field is E, charge is Q. So what will be the force on this charge? Force on this charge is given by Q into E, and it will be in this direction. Now this is a negative charge. Negative charge experiences a force in the opposite direction again, but magnitude will be same. Magnitude wise the force will be same, but the direction of the forces will be different. Now two equal and opposite forces, two equal and opposite forces acting on an object at different points creates torque. Okay, if this is happening on the same point, then they would have cancelled each other. There is no net force, there is no net torque as well, but because they are acting on 2 different positions along the same object, okay, it will create a torque. Torque means an effect of rotation. For example, you are pushing a door to open the door. So the door, when you are pushing the door, there is a torque acting on the door because the hinges produces an opposite force, hinges that on which the door is fixed, right? Now how to calculate the torque? Let me refresh your memories. Suppose this angle is theta. This is the angle between the electric field and the dipole moment. Dipole moment is from negative to positive. So dipole moment is along this direction and electric field is in this direction. So this angle is the direction between electric field and dipole moment. Now how to calculate torque? For that we have to find, first of all, our duty is to find the direct distance between these 2 forces. So one force was acting along this, one force was acting along this. So what is the direct distance between them? We have to find that first. How to find the distance between them? We will extend this line and we will draw a perpendicular. Okay, so this will give us the distance between this force and this force, right? So now in this case the angle is known, so that's why it will be easier for us to calculate. So this angle is theta, that means this is an similar angle, so this angle will also be theta. Okay, and this side is 2a. 2a is the distance between the dipole, so that is also known. This is 2a, this is this angle is theta, and this is a 90 degree. Because this is a perpendicular, that means this is a 90 degree. So right angle triangle, hypotenuse is 2a. What is the value of the perpendicular? Okay, so perpendicular is given by this distance, say L. So the value of L is given by 2a sine theta. Okay, sine theta is equals to L by 2a. Some people have curly brown hair turned permanently black. Some people have, some means sine, people means perpendicular, have means hypotenuse. So here this is the angle, that means this is the perpendicular, anything opposite to the angle is perpendicular. So perpendicular by hypotenuse is sine theta. So this perpendicular distance will be hypotenuse into sine theta. Okay, so L value is 2a sine theta. So we know the distance between the forces and we also know the magnitude of both forces. So torque is given by magnitude of any of the forces times the distance. Okay, this is the formula for torque. Torque is given by force into distance. Okay, but when forces occur in pair, then only torque acts. If there is only one single force, there will be no torque. Now force is given by Q into E and L is given by 2a sine theta, or we can rearrange them as Q into 2a into E sine theta. Now Q into 2a is a fixed quantity for a given dipole, and that is known as dipole moment. So PE sine theta is the torque acting on the dipole. So this is it, but after that we can write this same thing in vector notation as P cross E. Okay, P cross E is the vector notation. Now remember, sine theta always appears when there is a cross product. Okay, if it is a cos theta, then it would be a dot product. Also you have to remember, torque is a vector quantity, force and dipole moment, they are also a vector quantity. Your electric field is also a vector quantity. Now next, write any three properties of electric charge. There are only three properties of electric charge. Now this question can be asked as a 2 marker as well. So additivity of charges. Charges are additive in nature. This is the first property. Quantization of charges. All charges are integer multiple of smallest charge. E is the charge of an electron. Conservation of charges. Total charge in an isolated system is always conserved. So isolated system, you have to mention isolated system. And also if they ask you, add these lines. Many students add additivity of charges, quantization of charges, conservation of charges, but they do not explain what does it mean. At least add one line to explain what are the meaning of these things. Okay, now next, what is an electric dipole? Define electric dipole moment, give its direction. Okay, so dipole, two equal and opposite charges separated by a small distance is known as electric dipole. Dipole moment. Electric dipole moment is the product of magnitude of the charges and the distance between them. It's a vector quantity. The direction of dipole moment is from negative to positive charge. Write three properties of electric field lines. This is also very common, 2 properties, 3 properties, and even I have seen some colleges during their internal exam, they ask 5 properties. Okay, that is also possible. So electric field lines may start from positive charge and end at negative charge. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Two electric field lines are never intersect each other. Electrostatic field lines do not form any closed loops. Electric field in free space decreases as we move in the direction of the electric field lines and vice versa. So if you are moving in the direction of electric field, the value of electric field slowly decreases. Okay, and remaining of the points are self-explanatory. If you need any more explanation on this, please mention in the comment section of this video. Now let's continue. Define linear charge density. Mention the expression for electric field at a point due to an infinite line charge and explain the terms. This derivation we will do anyway, but this question is asked in your latest model paper. The linear charge density denoted by lambda is the amount of electric charge per unit length of the charged line or charged wire. Okay, mathematically lambda equals to Q by L. Q is the total charge, L is the length of the wire. So this is how you can define it. Electric field due to an infinitely line charge is given by E equals to 1 by 4 pi epsilon naught 2 lambda by R. Here you have to explain the terms. It is mandatory whenever you are writing an equation, try to explain what are all the terms. E is electric field intensity. So E is the electric field intensity at a distance small r. Lambda is linear charge density. Small r is the distance of the point from the line charge, and epsilon naught is the permittivity of free space. Okay, so this is how you have to write your answer. Now let's move on to the 5 marker section, long answer type 5 marker derivation questions. Derive the expression for electric field at a point on the axis of an electric dipole. So we will be doing 4 derivations, and from these 4 derivations you are definitely going to get, if derivation is coming from this chapter, you are going to get the derivation. So first is electric dipole. So diagram is compulsory whenever if you are doing a derivation. If the diagram is required, you have to draw the diagram. So here, as you can see, 2 charges, minus charge, plus charge is there. The distance is 2a. Suppose this distance is a, this is also a. Okay, this is the midpoint. So if distance is 2a, then this will be a, this will be a. The actual distance from the point where we are measuring the electric field, point P, the distance say R. Okay, so we are trying to find electric field at this point P. Okay, we are trying to find electric field at this point P. First of all, for a given dipole, dipole moment is given by small p equals to Q into 2a. So this is the dipole moment. Now first, how to calculate the electric field. So to calculate electric field, what we will do, we will find the electric field due to the positive charge and due to the negative charge individually, and we will try to understand what is the direction of these 2 electric fields, and then basically add them up to find the net electric field. So electric field due to this positive charge first. So what is the electric field due to the positive charge? Let me start here so that I can use this space. So electric field due to the positive charge first. So this is a positive charge, and we are trying to find the electric field over here. So we need this distance. So what is this distance? The total distance from the center of the dipole is small r, and this much distance is a. So this total distance is r, this is a. So that means this distance will be r minus a. Okay, so this will be r minus a. Okay, so E plus electric field, we know it is given by K Q by R square. In this case, R minus A whole square. So if you draw the diagram properly, it will save you time. Also, it will save you to understand the derivation as well. Okay, R minus A whole square. What will be the electric field due to the negative charge? So electric field due to the negative charge will be again K Q by, now in this case the distance we are measuring from this charge, so this distance will be, so this much distance is r, and if you add a value to it, you get the total distance. So this distance must be r plus a. So it will be kq by r plus a whole square. So the values of electric fields are known. Now next is the direction of electric field. So positive electric field is always outward. So positive electric field is always outward, and negative electric field is always towards, right, or inward. So negative electric field is always inward. Now what? So which one is bigger? So the electric fields are in opposite direction. So the net electric field basically will be, net electric field will be one minus another. Now how to find which one, which minus what? So for that we have to find the bigger one. Which one is bigger amongst these two? So electric if you confuse in the equation, then you have to realize that this positive charge is closer to the point. That means E plus must be bigger, E minus must be smaller. So in this case, what we will be doing? We will be doing E plus minus E minus. Now why we are doing negative? Because not because the charge is negative, because the direction of electric field is in the opposite direction. Okay, the direction of electric field is most important thing when you are trying to calculate the electric field. So E plus minus E minus, E plus value is given over here, KQ by R minus A whole square minus KQ by R plus A whole square. Now we have to simplify this. So KQ is common and we get R minus A whole square, R plus A whole square. This comes over here, R plus A whole square minus R minus A whole square. Okay, now what is R plus A into R minus A? That will be given by KQ. And one more mistake I made, not mistake I will say. So this Q is smaller in this question. So let me erase this and rewrite it once. Okay, so that there is no confusion. So this is small q, small q. Okay, so now let me put these values over here, and we realized KQ is common in both cases. So it will be 1 by R minus A whole square minus 1 upon R plus A whole square. Right? KQ is common. Now if you simplify this, you will get KQ. I always write capital Q, sorry for that. This is my habit. So KQ, it will be R square minus A square whole square. Okay, if you multiply these two terms, you will get A plus B, A minus B, that is A square minus B square, but there is a square common, so that is square, and in the top you will get R plus A square, A plus B whole square minus A minus B whole square, which is nothing but 4AB. So you will get KQ into 4RA divided by R square minus A square whole square. Now it's time for a small approximation. What approximation we will be doing? We will approximate that the distance R is bigger than the distance between the charges. Okay, and one more thing that we will be doing here is that K2A into Q into R, there is also a 2 over here, divided by R square minus A square. So what thing we have done? We have break this 4 into 2 parts. Okay, 1, 2 we have taken inside the bracket, and 1, 2 is outside the bracket. Okay, just a way of writing, right? 2 into 2, 4, still 4. And we have taken the assumption that the value of R is very, very bigger than A. So using these two things, we can write the net electric field is given by K is 1 by 4 pi epsilon naught. Now we have to write the value of K. Now 2A into Q is what? 2A into Q is our dipole moment. So this quantity, whatever is inside the bracket, is our dipole moment, and there is a 2 extra on the outside. There is an R over here, and in the division part, this A is very small. So compared to R square, A square is much smaller. So we can ignore that, and we can write this as R square to the power square, that is R to the power of 4, or this can be written as 1 by 4 pi epsilon naught 2p divided by r cube. 1 r cancels, right? So this is the expression for electric field due to a dipole on its axis. So if you do this derivation, full 5 marks you will get. Now let's next derivation, derive the expression for electric field at a point on the equatorial plane of an electric dipole. Again, diagram is necessary. Here, as you can see, this is the dipole, this is positive, this is negative. Now in this case, the distance is always measured from the center of the dipole. So in this case, this distance is small r. So let's slightly change. Okay, and this angle is 90 degree. That means this is a, this is r. So this distance must be equals to r square plus a square. Pythagoras theorem. Similarly, this will also have the same value. Okay, both will have the same distance. Now let us consider this positive charge. So what will be the electric field due to this positive charge? Electric field due to the positive charge will be k q by this distance square, that is r square plus a square. Square root, square, they cancel each other, so the only electric field is kq by r square. What about the negative charge? Negative charge will also be kq and divided by this distance square. This distance and this distance are same, so it will also be r square plus a square. Okay, so both distances are same, so we have put this electric field. Now if you see that both electric fields are magnitude wise same, what about the direction? So the positive electric field again is away from, positive electric field is always away from, and negative electric field is always towards. Okay, now in this case the electric fields are in complete different directions. Okay, so we cannot simply add or subtract, we have to add them vectorially. So for that, if we take components along this direction and along these two directions, then we will realize that the direction along y will cancel each other, only the direction along x will remain, and fortunately both angles will be same, because this is an isosceles triangle, because this is an along the equatorial plane. So if this angle is theta, this angle will be theta, and this angle is theta, this angle is also theta. Okay, these angles are coming in a different ways, but both angles are fortunately same. Okay, so we again will try to find the net electric field. Now we realize that positive and negative both have the same magnitude, so we will say E plus equals to E minus equals to E say. And what is the value of E? E is same as this value. So this is E, this is also E. What is this component of E? The angle is theta, so adjacent component is cos theta, and this is also E, this angle is also theta, this will also be E cos theta. So E net in this particular case will be 2E cos theta. 1 E cos theta from the positive, 1 E cos theta from the negative, they gets added and we get 2E cos theta. Now we will put the values of E as well as cos theta. So 2E value is k q by r square plus a square. Now what about cos theta? So let us consider this triangle. This triangle, this is the angle theta. Okay, cos theta means base by hypotenuse. Base by hypotenuse. So base is a, hypotenuse is square root of r square plus a square. Okay, so everything is done. Now again we have to just rearrange. K is common, q into 2a. Okay, so this 2 multiplied with this a, so q into 2a, and r square plus a square into r square plus a square square root, so we get r square plus a square to the power 3 by 2. Now again we will use the same approximation, that is R is greater than A. So in that case the net electric field will be 1 by 4 pi epsilon naught. This Q into 2A is our dipole moment. You have to mention that in the derivation, because I have mentioned in the previous derivation. I am not mentioning it in this particular derivation, but you don't make that mistake, and you have to mention that in the concurrent derivation as well. Okay, so this will be, and because we are ignoring this A, so it will be R square to the power of 3 by 2, so it will be R cube. Okay, so this is the net electric field due to a dipole on its axial plane. Now here you have to note that the dipole moment is from negative to positive, so this is the direction of dipole moment, but electric field is on the other side, right? So vectorially it can be written that net electric field is negative of 1 upon 4 pi epsilon naught P by R cube. Okay, this is one. Another way, also if you write it, the teacher will be impressed and they will give you full marks. Now next, derive an expression for electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss law. So we have a straight wire, infinitely long, charged, okay, say positive charge, and we are trying to find the electric field at some point P. So for that, first of all, suppose this is my P point, we have to construct an imaginary cylindrical Gaussian surface. Okay, an imaginary Gaussian surface of the distance. So suppose this distance is R, this will be R. The length of cylinder means it has to have a length, so length say L, and the charge density of the cylinder is lambda. Try to use a pencil and compass if possible to make this look better. Okay, now we will apply Gauss's law of electrostatics. So what is the Gauss's law? Gauss's law states that phi equals to Q enclosed by epsilon naught. Okay, again the definition of electrostatic flask says that if electric field, suppose here is given by E, and if we take a small surface area ds, then integration E dot ds is the flux, and if you take the integration throughout the surface along this entire curved surface of the cylinder, this is the total flux, and that is given by Q enclosed by epsilon naught. Okay, now you will realize why Gauss's law is very handy in case of symmetrical surfaces. So in case of symmetrical surface, what is the meaning of symmetrical surface? Symmetrical surface means if you stand along this axis and if you look around you, you will not find any difference, because it's a cylinder. Cylinder is symmetrical along the axial line. Okay, so if you look anywhere from that line, you will see no difference. That's why it is symmetrical. So if you can find any symmetry, then electric field will also be symmetrical. Electric field will also have the same value along the surface of all points on the surface of the cylinder. There will be no electric field along this flat surface and the bottom flat surface, but electric field will always present along the curved surfaces. Okay, so because of that, we can say electric field is constant, and we can take it outside, magnitude of the electric field, and then we write whatever is inside, ds equals to Q enclosed. Now what is the charge enclosed inside the cylinder? Charge enclosed inside the cylinder is basically the charge density times the length. Okay, so charge enclosed is charge density, line charge density into length is the total charge divided by epsilon naught. Now what is the meaning of this closed ds? Closed ds means the total surface area of the curved surface. Now what is the total surface area of a cylinder? Surface area, curved surface area of a cylinder is given by 2 pi r L. R is the radius, L is the length. So 2 pi r L equals to lambda L by epsilon naught. Or we can write the electric field is given by L cancels 1 by lambda by 2 pi r epsilon naught, or we can write it in a fashion 1 by 4 pi epsilon naught 2 lambda by r. This is a fancy way of writing, nothing new. So lambda by 2 pi r epsilon naught, we have multiplied 2 in the denominator and numerator, so this becomes 4 pi epsilon naught 2 lambda by r. Okay. Now last derivation from this chapter, state Gauss's law in electrostatics. Now statement I am not stating, it is already given in 2 marker section. Derive an expression for the electric field at a point outside uniformly charged shell. So here we have a charged shell. Shell means, what is a shell? Shell means it's a cover. Okay, inside is hollow, very thin shell, like egg, covering of an egg. So if you break the cover of an egg, inside the egg is there, but if there is no egg inside, if you make a small hole and if you take out everything inside that egg, then whatever is left, that is considered to be a shell. We have a charged shell. The radius of the shell, say, is given by capital R, but we are trying to find electric field at some distance, small r, and we are using Gaussian law. Okay, so now say the total charge on the shell. There is an advantage of this derivation. If this derivation comes, it is the most easiest derivation. The charge, total charge, you can consider it to be capital Q. Total charge on the surface of the sphere can be considered capital Q. Now what you have to do, you have to construct a Gaussian surface of radius small r. So that is the only thing that you have to do. Construct a Gaussian surface of radius small r, then we can apply Gaussian law. Again, this is a sphere, this shell is a spherical shell, and this is also a sphere. That means this is a spherical symmetry. So for spherical symmetry, what we can say, electric field and each and every point on this surface must be same. So due to So in the last derivation also, if you have to write that, okay, due to spherical symmetry, the electric field must be constant on the surface of the sphere. Right now, so as you can see, the derivation I have filled half of the board with writing. That means derivation is obviously not that big. So only thing that you have to do, phi equals to E dot ds equals to charge enclosed divided by epsilon naught. Charge enclosed is already mentioned. Now spherical symmetry, E is constant, so it will come out, close integral ds equals to q by epsilon naught. Now what is ds? ds is the surface area of this outer sphere. What is the surface area of a sphere? It is nothing but 4 pi r square, and that is equals to q by epsilon naught, and from here we get E equals to q1 by 4 pi epsilon naught q upon r. Okay, q upon r square, sorry. So this is the expression for electric field due to a Gaussian, due to a point charge. Okay, now let's move on to numerical questions, the most awaited section of this series. 2 point charges plus 4 nanocoulomb and plus 8 nanocoulomb are placed at the points A and B respectively, separated by a distance 0.2 meter in air. Find the magnitude of the resultant electric field at the midpoint O of the line joining A and B. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is replaced by another plus 8 nanocoulomb charge? So we will solve one by one. First, let us draw the diagram. So here we have two charges. One is plus 4. Let me change the color. Plus 4 nanocoulomb, and this one is plus 8 nanocoulomb. Okay, points A and B. Now separated by a distance 0.2 meter. Okay, now what we are trying to do is find the magnitude of the resultant electric field at the midpoint O. So resultant electric field at the midpoint O we are trying to find. So how to do that? The distance of A is obviously 0.1, distance of B is also 0.1, right? Midpoint total distance is 2.2 meter, so it will be half of that. So distances are known. Now we have to find the electric fields due to this plus. This will be in this direction and this plus will be in this direction, but because this charge is bigger, so what we have to do eventually, E8 and E4 we have to subtract them. That's how you can calculate the net electric field. So what is the electric field due to the positive 8 charge? So it will be K Q1 by R square. K is 9 into 10 to the power of 9. Q1 is 8 nanocoulomb. 8 into 10 to the power of minus 9. Distance is 0.1. So 0.1 square. 9 minus 9 cancels and we get 72, and 100 comes from here, so 7200 Newton per coulomb. Okay, divided by 0.1 square means divided by 0.01, that means multiplied by 100. Okay, so if you have any confusion regarding this, just check it once on your own. Similarly, E4 can be calculated as 9 into 10 to the power of 9 into 4 into 10 to the power of minus 9 divided by 0.1 whole square, that is 3600 Newton per coulomb. So what is the net electric field? Net electric field, as I mentioned, both electric fields are in the opposite direction, so there will be a subtraction, and subtraction will happen from the bigger minus smaller, that is 3600 Newton per coulomb. Don't forget to write the unit. Okay, second part, there is a second part. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is replaced by another 8 nanocoulomb charge? So if both charges are 8 nanocoulomb, in that case this is E8, this will also be E8. So part B is if plus 4 nanocoulomb is replaced by another plus 8 nanocoulomb, then both electric fields will cancel each other, right? Equal and opposite electric fields cancel each other. Thus, net E will be equals to 0. Okay, so net E will be equals to 0. Let's check the answer, 3600 and 0. Okay, now next question. 2 point charges 5 microcoulomb and minus 5 microcoulomb are located at A and B separated by 0.2 meter in vacuum. Again also almost similar question. What is the electric field at the midpoint O of the line joining the two charges? Here only difference is charges are equal and charges, one charge is positive, another charge is negative. Let's try this one as well. So this one is 5 microcoulomb now. This one is minus 5 microcoulomb. The distance is again 0.2, but again because we are calculating at the midpoint, so we will say this is point A, this is point B. So this is 0.1, this is also 0.1 because total distance is 0.2 meter. Okay. What is the electric field at the midpoint? Again we will calculate the electric field due to the positive and negative. Both electric fields will be same magnitude wise. Direction we have to check. K Q by R square. K is 9 into 10 to the power of 9. So say this is plus. Okay, plus 5 micro means 10 to the power of minus 6 and R square is 0.1 whole square. So 5 in the 45, 45 10 to the power of 3 plus 5, so it will be 45 into 10 to the power of 3 plus 2, 5. Okay, so 45 into 10 to the power of 5 is the electric field due to the plus 5. Similarly, electric field due to the negative 5 will also have the same magnitude. Now we have to check the direction. If they are in the opposite direction, they will cancel each other. So positive will be away from, negative will be towards. So in this particular case, both electric fields are in the same direction. That's why I say do not put the sign of the charges when calculating the electric field. That will give you a wrong idea. So first calculate the electric fields and then check the direction of the electric fields. Okay, so from this direction we can calculate the net electric field is given by 45 plus 45 into 10 to the power of 5, that is 90 into 10 to the power of 5 or 9 into 10 to the power of 6 Newton per Coulomb. So this is the net electric field. Okay, now what? Now is if a negative test charge of magnitude 2 nanocoulomb is placed at O, what is the force experienced by the charge? So this, the midpoint is not P, midpoint is O. So if you place a negative test charge, test charge is negative and that value is 2 nanocoulomb, what is the force experienced by the charge? So if you place a negative test charge over here, it will experience a force opposite to that of the electric field, that is towards A. So direction is confirmed because it's negative, it will be net electric field is in this direction. Negative charges always experiences a force in the opposite direction of the electric field, that is particularly in this direction. So part B, what is the net electric force? Force is given by Q into E. Test charge is 2 nanocoulomb, so 2 into 10 to the power of minus 9 and 9 into 10 to the power of 6, so it will be 18 into 10 to the power of minus 3 Newton. So this is the force experienced by the charge and the direction is towards or along OB, along OA. Why along OA? Because net electric field is in this direction. So the negative charge will experience a force in the opposite direction. So 9 into 10 to the power of 6 Newton per Coulomb is the net electric field and 18 into 10 to the power of minus 3 Newton is the resultant electric force. 3 charges each equal to plus 4 nanocoulomb are placed at 3 corners of a square of side 2 centimeter. Find the electric field at the 4th corner. Similar question came in your midterm paper. Okay, let's solve it. So we have a square and plus 4 nanocoulomb charges are placed at 3 corners, say this one, and say this one. Nanocoulomb is common. Now we are trying to find the electric field at the 4th corner, that is this point. Now say each side is given here as 2 centimeter. I am assuming each side is A for now. We will put A is equal to 2 centimeter at some point of time. Now, so electric field, how to calculate electric field due to multiple charges? Electric field due to multiple charges is you have to calculate the electric field due to the individual charges and then add them vectorially. So electric field due to this 4 is along this direction. Electric field due to this 4 is along this direction, and electric field along due to this 4 is along this direction. Now as you can see, because all the charges are same, okay, so this 4 and this 4 are in exactly 90 degrees angle, and their resultant will be along this direction, along the diagonal direction. Okay, this is only because these two charges are same. If they are not same, then it would be lot complicated than this one. Okay, so this is plus 4, this is plus 4, so this is the plus 4 due to this is the plus 4 due to this, and the first we will calculate the resultant between these two, and that is along the diagonal direction, and then we can add the electric field due to the corner one. Okay, what is this distance, by the way? This is A, then this will be A root 2, diagonal of a square. This is A, this is also A. Okay, and A equals to 2 centimeter or 2 into 10 to the power of minus 2 meter. Okay, so this one is given. Now first we will calculate the electric field due to this and this, both are same. Okay, both are same, and that we will say E1. So this is say 1, point number 1, point number 2, point number 3, point number 4. Okay, so electric field at 1 and electric field due to 3 are same, and that value is given by K Q by A square, or 9 into 10 to the power of minus 9. Q is 4 nanocoulomb, and A is 2 into 10 to the power of minus 2 whole square, or 10 to the power of minus 9 cancels, we get 9 into 4 divided by 4 into 10 to the power of minus 4. This 4 cancels, so 9 into 10 to the power of 4 is the these two electric fields. So this is E1, this is E2, this is E3, this is E1. Now magnitude wise both of them are same value. So what is the resultant of these two vectors? When two vectors have same magnitude, what is the resultant? Okay, and the angle between them is given as 90 degrees. So we know that resultant of two vectors A and B is given by A square plus B square plus 2AB cos theta. We have learned that in our PU1. So in this particular case both magnitudes are same, so A and B are same. So in that case A square plus B square, and this 2AB cos theta is 0. Why? Because the cos theta is 0. So cos theta 0 means 2AB is 0. So that means this is 0. Okay. Both are same values and angle is 90. So we get this as square root of 2A square, or A root 2. So when two equal vectors are at right angles, their resultant is A root 2. So when we add E1 and E2, E1 and E3, the net value of E13 is given by any one magnitude times root 2. Magnitudes are same, so that value is 9 root 2 into 10 to the power of 4. So this is the resultant of these two, and it is along the direction of E2. E2 and this quantity, they are in the same direction. Okay, so now the net electric field will be E13 plus E2. Okay, so E13 we have calculated. What about E2? Let me calculate E2 in this space. So E2 is given by KQ by A root 2 square. So everything is same, but there is only one root 2 square extra. That means only what we have to do, this KQ by A square is already known. KQ by A square is already known. That is 9 into 10 to the power of 4. But there is a extra root 2 square in division. Root 2 square means obviously 2. So that is 4.5 into 10 to the power of 4. Okay, so just put that value plus 4.5 into 10 to the power of 4. So 9 root 2 plus 4 root 5 4.5 into 10 to the power of 4. So if you put the value of root 2 and use a simple calculator, you can calculate this electric field is given by 17.22 into 10 to the power of 4 Newton per Coulomb. You have to use a calculator to get the final answer, and simple calculators are allowed in your PU board. Okay, now next. A conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 to the power of 3 Newton per Coulomb and points radially inward, what is the net charge on the sphere? So conducting sphere of radius 10 cm, you can recall the spherical shell derivation. So this was the radius, electric field we calculated. On the side, R is given by K charge on the sphere divided by R square. Now electric field inside the sphere is always 0, same as the spherical shell. Even though we have not derived it, electric field inside the spherical shell is also 0 because there is no charge. For a conducting sphere, all charges stay on the surface. That's why electric field inside the conductor is 0. Okay, so this is the formula that we are going to use. Okay, electric field is given, this distance is given, K we know, right? So E equals to K total charge on the sphere divided by R square. Now here you have to note that the electric field points radially inward. Radially inward means this must be the electric field must be negative. So this value you have to take minus. Okay, so radially inward means obviously the charge is negative, that's why it is negative. So we will use minus 1.5 into 10 to the power of 3. We will not use any negative sign in this unknown values. Okay, they will come automatically. K is 9 into 10 to the power of 9. Q is unknown. Distance is 20 centimeter. That is 20 into 10 to the power of minus 2 whole square. Now from here we have to calculate Q. Q equals to minus 1.5 into 10 to the power of 3 into cross multiply 400 into 10 to the power of minus 4. 20 square is 400 divided by 9 into 10 to the power of 9. Okay, so if you simplify this, you can calculate the net charge on the sphere, which will come out to be 6.67 nano coulomb minus 6.67 nano coulomb. Okay, the negative sign is missing over here, but there will be a negative sign. Okay, and if you miss that out, if you miss that negative sign, you will not get marks. They will deduct 1 mark. Okay, now next question. An uniformly charged spherical shell of radius 10 cm has a surface charge density of 16 microcoulomb per meter square. Find the electric field due to the shell at a distance of 20 cm from the center of the shell, 5 cm from the center of the shell. Now this question is from year 2025. Okay, there was a controversy happened with this question, because in the question paper, instead of giving micro capital C meter minus 2, what they have given? They have given this as, there was a misprint happened, centimeter to the power minus 2. So this actually means to be micro coulomb per meter square. That is the unit of charge density. But many students thought, what is this unit? So they started with micro or centimeter square, and they mess up in the middle of the question, and they started crying. So board says, okay, if you solve it by assuming centimeter square, or you assume it by micro coulomb per meter square, both solutions are correct, and they gave the marks. But many students thought, I will not attempt it and I will get full marks, but that did not happen. Okay, so first, uniformly charged spherical shell of radius 10 centimeter. So radius is given as 10 centimeter. And they asked you at two different positions. First is for 20 centimeter, second is for 5 centimeter. What is given here is the surface charge density. Surface charge density given as 16 microcoulomb per meter square. That is 16 into 10 to the power of minus 6 coulomb per meter square. So this is the surface charge density which is given. Now, if surface charge density is given, how can we calculate the total charge? To calculate the total charge, what we have to do? We have to multiply the surface area of the sphere, that is 4 pi r square, and then we multiply the surface charge density. This is the total charge of the sphere. Okay. Now, we know that electric field outside a shell at a distance, say capital R, small r, is given by, electric field is given by 1 by 4 pi epsilon naught, okay, q by r square. Okay, so if you put this value over here, the total charge, you will get 1 by 4 pi epsilon naught into 4 pi r square sigma divided by r square. 4 pi cancels, and you get this as sigma by epsilon naught r square by r square. This is another formula that you can remember, or you can come to this equation as I have arrived it. So sigma value is 16 into 10 to the power of minus 6. Epsilon naught is 8.85 into 10 to the power of minus 12. R square is 10 centimeter square. Now here unit does not matter. 10 square divided by 20 square, because centimeter square, they will cancel each other. 10 to the power of minus 2 both cancel. That's why centimeter is not super important. And if you solve it, this entire equation, you will get this as 4.5 into 10 to the power of 5 Newton per coulomb. Okay, so this is the electric field. And second option, this is first option, this is A. What about B? For B, the distance is 5 centimeter. So 5 centimeter is less than that of the radius of the sphere. So if it is less than that of the radius of the sphere, inside the sphere electric field will be 0. So inside the sphere electric field will be 0. So it will be 0. Okay. So last year's PYQ is also I have completed in this lecture. Now last question is from your model question paper. A positively charged spherical conductor of radius 0.1 meter produces an electric field of 1.8 into 10 to the power of 3 Newton per coulomb at a point P distant 0.2 meter from its center. Calculate the magnitude of the charge present in the spherical conductor. Okay, question is similar. Electric field is given, distance is given, and they asked you what is the charge on the conductor. Okay, so electric field is given by K, Q, by r square. Okay, so Q must be equals to E r square by K. Okay, E value is given 1.8 into 10 to the power of 3, and R value is given here as 2.2 meter. Just careful that this distance must be bigger than the radius. Radius hardly plays any role. For example, last question it did play a role to calculate the total charge. Otherwise, radius only you have to check whether it is outside or inside. Okay, divided by K is 9 into 10 to the power of 9. Okay, and you will get this as 8 nanocoulomb. Okay, so this will come out to be 8 nanocoulomb. Okay, now second part, also find the magnitude of the new charge produced on the same spherical conductor if 5 into 10 to the power of 10 extra electrons are removed from it. Okay, so here the direction of the electric field is not mentioned, so we can okay, positively charged is mentioned. Positively charged is mentioned, that means this is positively charged, so this must be plus. Okay, second, they are saying that you are removing electrons. Removing electrons means you are making it more positive. So if they say that you have to add electrons, then finally you have to subtract it. Okay, that means you are making it negative. In this case, you are removing electron means you are making it more positive. So by how much amount you are making it positive, that you have to calculate. So this is part A, this is part B. So we know that quantization principle, N into E. Number of electrons that you have removed is 5 into 10 to the power of 10, and we know that charge of an electron is 1.6 into 10 to the power of minus 19. So 1.6 into 5 is 8, and 10 to the power of 10, 10 to the power of minus 19, 10 to the power of minus 9. So this is also 8 nanocoulomb. So you make the sphere positive by another 8 nanocoulomb. So what is the net charge now? So net charge is whatever was the previous charge and how much positive you have made it. So 8 plus 8, that is 16 nanocoulomb. So the net charge of the sphere is now 16 nanocoulomb. So correct answer is 8 nanocoulomb for the first part, 16 nanocoulomb for the second part. This is from your model question paper that is there in this year. There is only one paper has a numerical question from this chapter, and we have solved it, right? And if you want to get more details of anything else, please mention that in the comment section of the below. Also, I would request you to subscribe if you have not yet subscribed. I will be back with more lectures very soon. Till then, bye.